Okay, then let's try to deepen our understanding, okay, about the linear regression. Okay, here let me run this again, just in case. Right, so you see that the true values for beta 1, beta 2, and beta 3 are 1, 0, 4, right, respectively. And you see that the estimates are very close to the true values. And also you see that t-values here, the first t-values for the beta 1 and t-value for beta 3 is quite large. Actually, their absolute value is bigger than 2, which means what? Beta 1 and beta 3 are statistically significant, right? But beta 2 is not, right? And this is very natural. Why? Because the true value for beta 2 is 0, which means what? The null hypothesis. In the null hypothesis, beta 2 is 0. And then now the beta 2, the null hypothesis is not rejected because t-value is not big enough to reject the null hypothesis, right? Okay, right? So then, okay, let me open this, right? Okay. So let's think of the case when we have very accurate beta hat estimates, right? So then the accuracy is measured by what? This variance of beta hat. So question is, when variance of beta hat becomes small, because the small variance of beta hat means accurate beta estimates, right? So this term will be small when what? When sigma square is small, or this inverse term is small. For this inverse term to be small, then x prime x should be large. Then what does it mean by x prime x? X prime x is what? This is sum of the squared independent variables, right? This is called variation of the independent variables. Variation is not equal to the variance. So variation is just sum of the squared independent variables, right? And this x prime x will be large when we have the large number of observations or the variance of x is large. Okay, so here the variance of x is determined by these numbers 10. Okay, so if these numbers are small, then we will have small. We will have what? We will have a small variation of x. Small variation of x means what? Large variance of beta hat, because this term is small, but here you can see inverse, right? So then if variation is small, then this inverse term will be large. So we will have the large variance of beta hat. The large variance of beta hat means very inaccurate beta estimates, right? Okay, so again, so to get very accurate beta estimates, the variance of x should be large. Or even if the variance of x is not big enough, once we have the large number of observations, still we will have a very accurate beta estimates because we have very informative data, right? And to see this again, let me try this again. Observation is 100. Instead, let me reduce the variance of x 0.5. Let me run it. Let me run it again. Okay, this error is 0.6, where true value is 4. Okay, but still I think this is good enough. Let me reduce it a bit more. 0.1 and 0.1. Here you see very large errors, right? True value is 0, but the estimate is minus 4.7, and true value is 4, but beta hat estimate is bigger than 7, right? Okay. But this, so then the variance of x is very small. But instead, if we have the large observations, let me say 10,000, and let me run it. Here, you see that the much more accurate estimates, close to 1 and much closer to 4, right? For example, say 20,000. Yes, very close to true values, right? Yeah. Okay. Let me go back to the original setting. So 100. And here is, let me say, 5. 5 is big enough, I guess. Let me run it. Yes, it's good, right? It's very, the estimates are close to our true values, right? But if we have a large variance, large sigma square means what? This is size of the noise. So if we have a large noise, then it's really difficult to see the relation between independent and dependent variables, right? So then let me say 100. Then run it, right? So then now error, the estimation error is bigger than before, right? So true value is 1, true value is 4, but errors are bigger than before, right? Okay. So then by doing this sort of the some we can deepen our understanding about the linear regression or some properties of the OLS estimators, right? Okay, right. And then before we move on, let me try the one additional independent variables. Actually, it was the homework though. Let me try. So we have one more. So then we need one more beta. Say true beta 4 equals, let me say 2 or minus 2. Yeah, doesn't matter. And then this is the vector of true betas. True beta 4. Alright. Sigma square is now say 2. And observations are 100. And then we need one more independent variables. Say x4. X4. Right? And then x should have x4 as well. Is there anything to change in this line? No, nothing to change. What about this? Yeah, nothing to change. All right. And what about this? All right, nothing, right? Nothing. And what about this? Yes, there is one thing. Now this number should be what? Should be 4. Okay. And here there's nothing to change and nothing to change. And actually this is now 4 by 1. And t values must be 4 by 1 as well. And here is output, right? Then let's run it. Yes, so these are the estimates. So again, so if you have the same RNG number as mine, then you will get the same outputs. Of course, you should have the same true values and the same number of observations, right? And you have the same you have the same independent variables, right? Okay, right. This is now t by 4. Okay. All right. Okay. Now just suppose you wanna change you want to change to the case of the 5 independent variables. Yeah. I'm not going to do this. Just let's just imagine. Okay. Then if we have to try 5 independent variables, then you will have one more beta coefficient, and then you will change to beta. Then E will be 5 by 1, 5 by 1. In this case, 4 by 1 though. And then you will add one more independent variables, right? And you will change this line. What about this? In this part, you will change only this number and nothing else. Right? Can you see anything at this point? So, regardless the number of independent variables in this section, right, which is estimation part, there's few things to change. Only this and nothing else, right? Nothing else. Which means what? This code is very generic to the number of independent variables and number of observations, right? So this code can be used generally, okay? Generally, right? Okay. Before we finish, let me run it again, just to make sure it runs, right? Okay. Right.